So today we had 15 talks on various aspects of small scale dark matter constraints. And so Dennis and I sort of organized these into about 5 different themes. So there were a chunk of talks on predictions from different dark matter models, some cosmological, some not. So those are in this blue box here. There were a good chunk of talks on whether we think we really understand what's going on other than dark matter, which shows you sort of where we are with that. And then there were also a good section of talks on analysis of particular streams, on what types of signatures we might expect and how we would extract dark matter information from those in principle. And then there were 3 talks that were that proposed alternative probes of small scale substructure, and there were a few that weren't in here that we'll get to in a second. So thank you to all the speakers for preparing this set of talks, which I think really spans the space well. So we're gonna pull out each of these themes and discuss it a little bit, and then that hopefully will prompt some discussion, because the themes that people talked about actually matched up pretty well with a lot of the questions that were posed in the Google forms that you all submitted on this topic. So the first theme that we identified was, what predictions can we make for different dark matter models? And the work shown in these talks and in other work on this subject has, I think, pretty conclusively now shown that different dark matter models do predict different signatures for stream interactions on a number of fronts. But we also, as people pointed out in their talks, and as I know firsthand, is computationally challenging to model these interactions directly by putting streams into a simulation that has all the stuff in it that you need, both because there's a staggering dynamic range issue, and also because in some cases, incorporating the model of dark matter that you have picked is computationally challenging. So like a good example of that is fuzzy dark matter. So baryonic effects also alter the situation significantly in the volume where we have the most data from Gaia at the point where we are now. Specifically, the existence of a galaxy increases the tidal forces available to disrupt substructure, and changes the dynamical time slightly, as well as sort of imprinting a particular symmetry on the potential there that isn't present if you don't model the disk in some way. And so this has been shown pretty conclusively now for Lambda CDM. And I am not as familiar with what's been explored here for other models, but I would expect it to be similar since we know there's a galaxy in the middle of the galaxy. And then there are some models that are represented here that I think could still be explored. I've been thinking recently about SIDM in this context. And so you guys asked a lot of questions about this in your form filling out. This gives a good way for discussing what the importance of idealized versus cosmological simulations is, because the set here and the work that people have done in this room is about 50-50. And I think that the next question goes into that, which is like down to what mass scale have we really converged on what we expect for substructure in the Milky Way? I think that qualifier is important because I think that's that the main concern for a lot of people is resolution here, although there are some others like baryonic effects. And those are all mass dependent. So I think it's important when we talk about that question to qualify it with a mass scale. And I would add, actually, now that I think about it, do we need to converge to a lower mass scale than we have already in order to make good predictions for what we would see in our streams? A related issue, how much scatter do we have in the predictions for our Milky Way substructure, given that we are not certain of the Milky Way's fundamental properties? For instance, the number density of subhalos as a function of mass depends linearly on the mass of the Milky Way. So And then I added, and Dennis added a couple extra questions here. One is, if we predict these different signatures, how differentiable are they with our current observations, and what kind of information do we need to do any better at differentiating signatures of one dark matter model from another? And what about modified gravity? Are there predictions along these lines in those models? All right. There were also a lot of talks on whether we're sure we understand what's going on other than dark matter. And many of these talks made points that a lot of non-dark matter things can mimic the effects you would expect from some halo interactions. So there was one talk that pointed out that if globular clusters, as we think a fair portion of them might, accrete as part of satellite galaxies, then that can pre-process them and change the expected velocity dispersion for their tidal streams. The streams can be perturbed by interactions with not only dark substructure, but luminous substructure in the galaxy. And Mark Helis's talk made a good point that black holes can shape the phase space distribution of the progenitors of globular cluster streams. And so we need to worry about that now, like magnetic fields. Things that people didn't talk about in their talks, but we are aware also can do this, are things like bars and spiral arms and orbital resonances thereof, or even just in the general potential. I think yesterday's session had a talk from Tomer on this, and giant molecular clouds. And so a lot of these effects are dependent on the type of progenitor or the orbit that the stream is following. And so we need that information in order to start to untangle this and determine whether the density variations, as in this first question, are caused by the progenitor or by a perturbation from dark matter or by a perturbation from something else. So the big questions that you all identified that we didn't have to were things like, what do we need to know in order to rule out other things but dark matter? And do we have like a complete catalog of all the things that we know could do this? And those contribute to the final question, which is really, how do we make models in realistic enough potentials with realistic enough progenitors that we can be confident that we're disentangling these effects from one another? All right, so I'm going to stop there and let Dennis take over.
Yep. So after those, we kind of saw a bunch of talks on what are the signatures of perturbations in streams. So now there's been many streams that have been observed which have signatures that aren't consistent with being in a kind of smooth potential. So in Kian's talk, we saw perturbations to the stream track and the density. So there were wiggles in the stream, both in the density and in the actual track itself. This wasn't really discussed in any single talk, but there's also the morphology of the stream. I guess this was mentioned in Malhan's talk in terms of the spur and the blob, as well as the kink in the Atlas stream. So there are streams with like very significant perturbations, which we don't fully understand how they arose. There's also the velocity dispersion. So measuring precise radial velocities is really helpful. Megan had a nice talk showing for GU1 how it looks inflated a bit. And then the stream width from Kyate's talk on how the cusp versus core can affect how stream widths look for globular clusters originally inside dwarfs. And the kind of questions that have been arising both on day one and then throughout, the questions you all asked in your Google forms, what kind of precisions do we really need to measure each of these quantities with in order to really be able to constrain dark matter? Similar question about where in the galaxy are the most useful streams for measuring small scale structure? So this is kind of the third point is kind of something which has arose over the last few years, which is interesting. For every single stream we've looked at really carefully, they're all perturbed. Like there's no like really nice clean streams which look perfect. They're all weird in some way. So is that weird? And then similar, kind of related question, which of the observed streams currently have unexplained features? And there's many such streams like that. Next slide. So then we talked about, there were a bunch of talks on how we can actually extract dark matter content from streams. So there's kind of several approaches that have been built up over the last few years. So one is this power spectrum approach, which Neil Bannock talked about, where we can look at the kind of statistical fluctuations in a stream and measure that, which is a really promising technique. There's also an approach which Tarek Hilmy discussed and Jirakova also discussed about fitting individual features in a stream, such as perhaps asymmetries or the kink in the Atlas stream. And then there's Kyati's talk, which also relates to this, about using the kind of width and dispersion of the stream to try to infer something about dark matter. I will say that, I mean, Kyati's talk is more about, you know, the dwarf that the globular clusters fell in with than a subsequent perturbation from other effects, but it's kind of in a similar vein about measuring dark matter properties. There were some really nice questions, very thought-provoking, I think, about from you all. You know, are streams too messy to be used for dark matter study? I think before the last few years, I thought the answer to this was no. You know, having seen all these really perturbed streams, it is getting, you know, it's getting interesting. There's lots of things you have to worry about when interpreting things. I put this question here again about where in the galaxy are the most useful streams. I think it's just good for thinking about, you know, which are the streams that we really trust, what kind of orbits are they on. I think the last two questions are also really important to think about, you know, kind of the impact of the work that we're doing. I mean, what will it take for the broader community to really trust what we're measuring? So there's been many constraints now on, you know, the mass of the warm dark matter particle. And I think just about understanding what it takes for that to be really trustworthy. And a similar question, you know, can we ever reliably detect dark matter subhalo with a stream to really prove to the community that we're seeing these visible clumps of dark matter? And then the next slide. And finally, yeah, we talked about alternative probes of dark matter. So there were many talks about this on lensing. So there's really promising work with strong lensing and flux anomalies, where we can, you know, see dark matter substructure at high redshifts. Milky Way satellites are another really good probe. This was mentioned on I think yesterday, about the kind of using the acceleration of stars with radial velocities to measure substructure, which is really crazy. But with next generation spectrographs, it should be possible to actually directly see accelerations from subhalos, hopefully. There's also pulsar timing arrays and Lyman alpha forest for measuring small scale structure. Yeah, so I mean, one question about this is, you know, which of these probes is the most sensitive to small scale dark matter? There's no single answer to this. I think many of them are quite competitive right now. How can we combine these probes? So Beerer had a nice talk talking about a kind of consistent framework of combining satellites and the flux anomalies. But it could be cool to try to combine everything into one framework and get, you know, the tightest constraints. And then a similar question which was asked about, you know, what is the complementarity of stream measurements versus lensing? Because they're quite different in terms of what's known locally versus at high redshift, and kind of what are weaknesses of each of these. So yeah, those were the kind of discussion points that we would like to get started with. But we think that these five, again, this is the kind of second slide Robin showed, but this just shows the kind of overall questions that we think were asked, and kind of probed with the talks from today. So we're going to leave this slide up just as a kind of something to spur discussion.
Alex, you raised your hand.
Yeah, I'd just like to chime in here that we're all super interested in measuring the subhalo mass function below the threshold of galaxy formation through perturbations, but it's worth keeping in mind that sort of the completely smooth stream, the completely unperturbed stream, is the discovery that's going to be super interesting, because lambda CDM and all the baryonic effects are introducing perturbations. And if you find something that is completely smooth and unperturbed, that's really hard to understand.
Yeah.
Is that a challenge?
I think it is.
Yeah, sure.
We're trying.
Question is, if we, you know, a lot of the streams we're going to be discovering are going to be farther out in the halo, you know, with Ruben, with Roman, and
yeah.
then the question becomes, if we start finding these really smooth, uniform density streams out there, you know, what can we say on a statistical basis about what the subhalo interaction should be?
Sarah.
Yeah, I was just going to chime in and say that at that point, it'll also be hard to convince ourselves whether or not we've seen the full extent of the stream, or if we're just not probing the messy, low density parts.
Yeah, and that one of the things, I'll comment on that, for satellite streams anyway, one of the things we're finding is that I think it looks like we may be missing quite a lot if you compare the sort of typical lengths of streams that you find in cosmological simulations that are generated by satellites from the ones that you see in the actual Milky Way. But that is a very non-quantitative statement right now. That's me eyeballing things.
Cool. So should we go ahead with kind of summarizing what each room chatted about? So let's start off with room 1.
Yeah, I can share what room 1 had. We talked a lot about the effects of what dark matter or different dark matter profiles might have on streams, and especially visible effects, as well as what effects we can expect to see from things like baryonic effects or orbital resonances or things of that nature that we can also predict that wouldn't be dark matter related necessarily. So essentially, just because you can see a perturbation in the stream and because you can model it as some kind of dark matter interaction or as some kind of non-dark matter interaction doesn't necessarily mean that that's what it is. And we also then spent some time talking about cosmological simulations, especially the Fire 2 sims, and what we would need in order to get better grasps on what effects are actually dark matter related within that regime. And we also talked about the future of information from other galaxies, especially Andromeda, that would help us infer things about the dark matter content in the Milky Way, especially because the Milky Way is fairly unique with its current LMC and fall situation.
Very cool. Room 2.
I'm gonna, I guess I'll summarize some points. So we talked a lot about whether streams are too messy to put powerful constraints on dark matter or not. And so we talked about what we mean by messy, and we had some good optimistic younger folks in the room who said, no, everything will be solved. But I think one key point is that even though we're finding more and more dynamical effects that can mask signatures of dark matter substructure perturbations and things, we're also finding a lot more streams thanks to many of you. And so there's some ideas for how we can leverage the population to try to disentangle all of the different things that are happening, looking for streams that are on similar orbits and doing sort of pairwise differences or differential type comparisons between streams. And then we talked a bit about the point Alex raised just after the introduction, Alex Jolicoeur-Wagner, and the fact that we're finding every stream that we look at in detail is perturbed in some way is kind of the least interesting result that we could have found, because it kind of goes along the same path of, well, it could be lambda CDM. Whereas if we found everything was perfectly smooth, all the streams were perfectly smooth and boring, that would be an even stronger statement. And then lastly, we talked a bit about what would it take to say to people, we have found evidence for non-lambda CDM dark matter in the Milky Way. And so we talked a bit about that, at least for the GD1 spur, we seem to, from the models that Anna and we were doing, seem to require a very dense object. So if we can find perturbers and characteristics of those perturbers that are inconsistent with what CDM can produce or other dark matter models, maybe that's the way forward. But we need to find multiple signatures, not just one stream.
Very cool. I guess if there's kind of, how long does this particular part last, Adrian? Like until we go into the wonder.me rooms? Is it like
until about quarter past?
Yeah, and we don't have to go room by room. We can happen organically if people want to respond to things that were raised already, whatever.
If they want to say, people like want to comment on perhaps what was just discussed, then they can raise their hand. If not, we'll just go room by room. So Sarah Pearson has raised her hand.
Oh, I was just going to summarize room 5, if that's all right, because it's
cool.
very related to what Adrian just said. So we also spent a lot of time just discussing at what point will we convince ourselves and the astronomical community that we've constrained anything about the particle mass of dark matter. And then we went into a lot of discussion on details versus numbers of streams. So GD1 is this ideal candidate because it's retrograde. and not as affected by baryonic components. But then there's the problem that we don't really know the progenitor of GD1, and we discussed how that could affect what we interpret. And then we also just thought with more streams, and we don't necessarily need kinematics, when we just go back and think about, for example, Andrew Wetzel's talk, that there's some information in just the distribution of dark matter subhalos, and maybe just the number of gaps we'll see in streams with galactocentric radii, and that might help if we go to other galaxies than the Milky Way. But we definitely spent a lot of time discussing the fact that we don't really at this point have an answer for should we just have more streams, and we don't in the Milky Way, like GD1, with a lot of detail where we can go in and do really cool analysis like Bonazza 2019 and really trace out what type of subhalo could create a gap, versus just having a lot of gaps in a lot of streams and looking at statistical properties. And I don't know, we talked about a lot of other things, so my group should feel free to chime in.
Cool. Yeah, I guess, yeah, in that context, I think, yeah, the kind of power spectrum ideas are really cool for tying in together many different streams and are kind of a statistical way to count out the gaps. Which is quite nice. Rohan has raised his hand.
Yeah, as someone chiming in from Sarah's group, I think one interesting added baryonic complexity to the interpretation of these complex morphologies arising from Kathy's talk that he showed about how, you know, these streams that have been processed in the in their host dwarf galaxies before being accreted show markedly different features and complex morphologies that we need to be able to be able to discern the difference between those effects, the effect from this processing and the history from the dwarf galaxy it once belonged to, versus like whether we are seeing interactions with subhalos and so on and so forth, is another layer of complexity that we need to grapple with in order to like convince the community that we're actually like, you know, seeing this is lambda CDM subhalo versus, you know, well, maybe it was in a massive, like, you know, dwarf galaxy that underwent some sort of merger, and that's why we are seeing this puffing or this particular tail and so on and so forth.
Other rooms. We've got 1, 2, and 5 so far. We have other people with relevant comments. Mike Peterson has raised his hand.
Sure, I can report on. This is room 6, and we spent a lot of time on that same question of trying to frame it, thinking about, do we need to understand sort of the globular clusters from birth to understand the nature of a lot of these stellar streams, and what we would need to do to distinguish this observationally to some necessary level. We kind of came to a consensus that we would want to look at the globular cluster streams to distinguish between different dark matter models. And then the key question is whether we can rule out features coming from internal dynamics, and maybe just summing that up as the relative impact of external versus internal. We touched on 2 other things, just asking the questions about what masses of subhalos we're looking for and what impact those are going to have on streams. And then a practical one about a question of, are there easy tools out there to predict how streams would react to fluctuations from different dark matter backgrounds?
Very cool. Kind of more related topics. I guess maybe Mark Helas, if he's still here, or someone from the room I was in. I've forgotten the number now, but we had some nice discussions on.
I could summarize room 7, since I was taking notes there, and a lot of our discussion in room 7, it sounds like, was very similar to many of the other rooms. A lot of it centered on the essentially on the modeling of globular cluster streams, and questions about whether, you know, we need to be concerned about two-body interactions within the streams. Are we missing important physics by not doing full in-body, and not including simultaneously all possible baryonic effects? And I guess we kind of, many of us agreed that looking at binaries in streams is a really interesting way forward. And then one other thing related that we discussed, I guess we also discussed the power spectrum and its its constraints on fuzzy dark matter, for example. And one other thing that we were talking about briefly was whether, what are data sets that we can do with this? And I think we could probably discuss this in more detail on Friday, but we were discussing, for example, LSST proper motions. Do we have to wait until the full 10-year survey to have the precision to study streams, at 23rd mag with LSST? And I guess, I think not necessarily, because even with the first year LSST depth, we could use DES and Delve and other surveys as a first epoch and get reasonably good proper motions, but to get really good Gaia-like proper motions, probably 10 years. And Dennis, I guess you can fill in anything I forgot about.
Yeah, no, I think that's really good. I think, yeah, we talked a bit about the kind of how well we have to be able to follow disruption of globular clusters, and kind of Mark Helas's talk, and how that kind of picture can impact, let's say, Kyati Mahan's result about the disruption of a globular cluster in a dwarf galaxy, and kind of doing that fully self-consistently with collisional codes. So like Mark Helas uses N-body 6, which follows the kind of stellar evolution and the kind of orbits of individual stars near each other, while most of the rest of us, myself included, model globular clusters with collisionless codes like Gadget or other collisionless codes, which don't really account for all of those effects. So just kind of making sure that we really understand, let's say, the kind of framework of a dwarf and a globular cluster falling in together.
Alex said he could summarize for room 3.
Cool.
Yeah, so I was in room 3, and I'll try and summarize some of the notes from that. So we started off talking a bit about wide binaries in streams, and the relative contributions of sort of force and the derivative of the force, or the tidal force, and how the two have different distance dependences. And so they may actually have different dependences on subhalo masses. In other words, more massive subhalos could affect the force more, so larger gaps and disruption, whereas tidal forces and heating may be affected more by the smaller subhalos, which have a closer passage to the stream. So we talked about that a bit, and that sort of brought us into the idea of streams of 2, which I think is a tagline from Adrian, and the idea that, well, finding these correlated stars correlated in phase space could be very useful because they could be very weakly bound and very sensitive to disruptions from small substructure. And then there's an offhand comment about there also being galaxies of 2. If you think about the Willman and Strader definition of a galaxy theory. And then we talked a bit about the influence of the LMC and whether the subhalo population of the LMC, as it falls into the Milky Way, would alter the phase space distribution of subhalos in the Milky Way, and whether that could be detectable. And sort of the soundbite there was about supergalactic civilizations firing dark matter halos, alien dark matter halos at us from the LMC. But realistically, there is a question about whether this the LMC would have an influence on the subhalo populations below the threshold of galaxy formation, and whether that should be taken into account. And then we talked a bit about beyond lambda CDM models and their complexity, and sort of as we dig deeper and deeper into fuzzy dark matter, for example, we start seeing details that maybe that make it more difficult to interpret than just a suppression of the subhalo mass function. And there's a question about how deeply we would need to dig into other beyond standard model dark matter ideas to really rigorously predict what influence they would have on subhalos and stream dynamics.
Cool. Guillaume Tomas has his hand up. Go for it, Guillaume.
I'm going to report for Breakout Room 4, and I will try to be quick because I can speak of that for the whole day. So one of the things that I was mentioning, for example, in the room was what kind of feature should we be focusing on? Should we be focusing on gap with density variation? Should we be focusing on kinematics of the stars? I'm absolutely convinced that we have to go for kinematics because gap variation can be created by many things, including observational feature. And at some point, it's hard also to understand completely the observational feature in all of these big surveys. It's extremely complex, and selection function also impacts them a lot. So it's going to be complex. I'm really persuaded. It's really my own opinion, but we have to go for high resolution spectroscopy to really get less than 1 kilometer per second precision individual measurement for stars in that region. Also, what we're mentioning is, yes, the impact of the LMC, but this time not with the sub-low population, but just by the presence of this big LMC that can perturb the global potential of the Milky Way. And this kind of modification of this potential can also create some resonances that move with the time, creating some locally or temporary resonances region where it can also create this kind of effect, which will not be linked directly to an object, but will be linked to the LMC in full by itself. And this is extremely dependent of the orbit, of the mass that you take, and all these different features that you have as well. The other thing also was where should we be looking for the ideal streams to be able to look for this feature. And well, we didn't went to a consensus. Ideally, we would like to go far away, but if you imagine that there is a LMC, the Sagittarius are on kind of a perpendicular orbits, and with the Sagittarius also orbit that have been modified recently by the LMC, which part of the halo basically is still to be unperturbed and is kind of perturbation free. And the question is also, how sure are we in the model of the perturbations that we're going to put? Like even for the bar, for example, we don't really know for sure, and there is a lot of discussion in the disk community for the length of the bar, for example, and for the mass of the bar. So how good are we to be to put that in the model, and what are the different features that we have to try? And I'm absolutely convinced that if we want to try to detect the dark matter with density variation, especially, we have to model everything. But yeah. Again.
Thanks, Guillaume. Very cool. I guess just to echo your point, I mean, one other really kind of unique prediction from perturbations is to have like the features off stream. So for example, like the GD1 spur and blob, and having the kind of kink in Atlas. So there are kind of, in addition to kind of track variations, there's also these kind of morphological features which can't really be created by a survey unless it's kind of crazy selection effects. I guess any more comments from rooms about things we haven't discussed so far, or kind of viewpoints that you want to bring up that didn't quite align with the current discussion? I think we've heard from about a bit more than half of the room so far. Orlin, go for it.
Yeah, so I've been volunteered for our group, and I guess we mainly talked about some points that have been mentioned already about which constraints can streams actually bring us, and the fact that we need more theoretical work to be sure to find out what we can use streams specifically for. We talked about in the last 5 minutes also about the LMC dark matter wake that we could look at to study the dark matter candidates, but also that there has been work suggesting that we need a very high resolution in codes as far as one solar mass, so that we should be maybe looking into analytical work to get into that regime. I think that's a basic summary. Maybe someone wants to weigh on it, but that's it.
Awesome. Any more kind of discussion points? There was one kind of discussion point that I think I'd seen raised in chat and a bit elsewhere that we didn't discuss yet, and that has to do with like how much can we trust cosmological simulations and the kind of subhalo properties in CDM. So there's some work by like Raphael Irani and Frank Vandenbosch showing that the kind of full disruption of subhalos doesn't happen if you have really, really high resolution. And so you can always get these kind of inner parts of the, let's say like NFW subhalo remaining. And so like, what is the effect of these many very small ones? Like, is that a real thing, or is that something wrong with their argument? Because obviously, like in most of the you know, cosmological simulations, you don't kind of like, you do fully disrupt. But, you know, I guess Frank and Rafa would argue that that's not quite correct because they don't have the resolution. So I think another important point to think about how much we really trust the large scale simulations. Yeah, I guess Jeremy asks what it counts as the full disruption of subhalo. Yeah, I guess, I mean, in a subhalo finder, then you stop finding it, but also there's kind of nothing remaining there. But while in the work of like Frank and Rafa, you always have an inner part remaining. It's kind of quite low in mass though.
Yeah, I think this topic. I had a few questions for the people that are doing the analytic simulations, like or the constrained simulations, like Raphael, the numerical experiments. I wonder about some of the assumptions in those because they don't seem to jive very well with what we see in simulations where you have cosmological initial conditions. Just because you have to account for the fact that the orbit is changing, not just from dynamical friction, but also because the galaxy is assembling and growing in mass. And that changes the orbit and usually will bring the subhalo into a place where the tidal forces are stronger and stronger. And so if you don't model that right outside of the cosmological context, then I'm skeptical about what you can conclude about, even at infinite resolution, about the end state of a subhalo. On the other hand, I think there's a point after which it doesn't really matter whether you resolve it or not, because it no longer is massive enough or like just massive enough to change the streams that it encounters at all. And again, because dynamical friction is built on density contrast, if you're not simulating that, then you're not going to get the central densities right. So I think there's still some work to be done in this area. And I don't know the work that people have done on the numerical experiment side as well as they do. So I'd like them to talk about this a little bit. But going back to Jeremy Webb's question in the chat about what counts as full disruption, I think this is where we might need to synchronize our terminology a little bit, because when cosmological simulators talk about that, what they mean is that the density contrast with the background galaxy is low enough that it can't be differentiated by the halo finder anymore. But that doesn't necessarily mean that there is no density perturbation there at all. It's just that it's not big enough for the thresholds that you're setting in the halo finder. And it generally refers to the dark matter part of the simulation. And when you have hydro, a lot of times you see that you lose track of the dark matter, but you still see the stars. So, so there are a lot of like details in this part that I think we need to synchronize a little bit on between the numerical experiments, which I agree are doing some convergence testing that we can't necessarily do in cosmological simulations, with the stuff that we're doing in those cosmological simulations. So I think there's still some dialogue that we need to have here before we pronounce everything unreliable or not.
Should we let perhaps Rafa respond to that, and then maybe we go into the wonder.me just so we can have our coffee break? So let's, Rafa, why don't you respond to that point?
Yeah, thanks a lot, Robin, for the comments. There are many things you said which I agree with. I'm not too worried about dynamical friction, especially for the low mass subhalos like 10 to the 8, 7, 6 solar masses. But for the more massive ones, I absolutely agree. We need to take this into account because it does drive satellite galaxies into regions of stronger tidal field. For me, the critical question right now is what's actually the inner slope of primordially formed cold dark matter halos? Is it -1 till the very center? So do we really have this adiabatic protection due to the orbital frequencies, which get smaller and smaller going to the center, and hence stop subhalos from disrupting in idealized simulations? Or does dark matter actually behave more like a NASTO or like tiny cord, and not completely self-similar density distributions, because in that case, even qualitatively, the tidal evolution is very different, and there is no such convergent remnant state, because once there is a core, energy is absorbed differently and much more efficiently, and there's no adiabatic protection of the very inner regions. So I absolutely agree, dynamic friction is important for the massive systems, and using my toy models on heavy dwarfs is not a good idea, at least not without manually adding dynamic friction. But what I would ask is, do we actually, like, how good are our constraints, and how good constraints can we get to better models on how cuspy cold dark matter actually is?
So in the last slide, we added a slide on the end of the presentation from this morning. And there was a lot of lively discussion when we came back together about several things. But we sort of encapsulated them in these two themes. One is the baryonic effects on streams, and the other is the effect of dark matter substructure. And so we're going to have two rooms that one discusses baryons and one discusses dark matter. And we want both rooms to report back on the same two questions or variations thereof. The first is, what evidence would convince you that the type of effect you're discussing was not that, right? So if you're in the baryons room, you have to decide what would convince you that a jiggle in a stream of whatever sort was not baryons. And if you're in the dark matter room, you have to discuss what would convince you that it wasn't dark matter. And then what advances in observations and theory do we need to get to the point where we would have that kind of evidence? Because that's really the big question that we're tackling as a whole. So you can keep this slide open if you want to do that, but then we'll just let everybody go into the two breakout rooms, I guess now, is that right? And then you can have at it.
Over that kind of time scale, but in every example we've seen, the main effects are kind of deflections of streams. SAG is different. SAG can pass close to things. So in my talk, I talked about, what Phoenix and like Atlas and GD1 look like with SAG, and in the past we'd seen SAG creating features in GD1 and Atlas just based on randomly rewinding its orbit. But now we're trying to do more consistently by taking Eugene Vasiliev's fits to SAG, which give us a way better understanding of its history, and then following that disruption. And so there, yeah, we do see a few streams which can have features, like Phoenix can be hit by SAG, as an example. But yeah. Pao.
Yeah, sorry, a little of a side question, but following on what you just said, I think I commented this with Adrian in yesterday or something like that. I was just wondering, do we know where the dark matter that has been stripped from Sagittarius goes to, and what it's the expected effect on other streams that just happen to cross that area of the sky?
I guess I can take this one as well, maybe. But yeah, so in the models that I showed from Eugene's SAG fits, we are going to follow the dark matter there. So Eugene did include dark matter within his disruptions. So we're gonna add that dark matter back into the things I was showing, and have a look at where the kind of dark streams of SAG go. So Joe Bovey had a paper from 2016 where he showed that, in principle, the same way that perturbations of subhalos make features in streams, the kind of long dark matter streams also do it. It's the kind of point that also Sarah was making, that it's like, even though it's long, if you pass through it or it kind of swings through you, then you can still get a very large, well, not as big as something really compact hitting you, but it's still an effect that can be seen. And so we need to look at that. And then also, Adrian done some work on GD1 showing that there could be subhalos orbiting, in SAG's orbital plane, which could have created a GD1 feature. So it's also worthwhile to put subhalos in the outskirts of SAG and see where they go and if they can do it.
Yeah, exactly. Just saying that the smooth component might not be enough, but if there are some clumps in the dark matter component, that could be.
Yeah. Sarah.
Yeah, I kind of have a topic change a bit, a question for the power spectrum people in the room. So I'm just curious, what state do you people think we're at in terms of understanding the bar and the disk and all these heating components from baryons in order to use this technique on multiple streams? So do we need to know the orbits of the streams better to just apply this technique to more streams? And where do you think we're at in really understanding the effect of how baryons are puffing up or creating density variations in the streams?
Is Neil Vanek in this room? Yep, Neil, go for it.
Yeah, so thanks for the question. Yeah, so I think to model the effect of the bar, spiral arms, and the GMC, we have to know like the full 60 phase space information so that we can orbit model these streams and, you know, to whatever dynamical age that we want. As far as testing the PAL5 is concerned, we actually tested different models of bars and also for spiral arms, including like a 4-arm spiral arms, which we found to impact the stream in a much more severe way than a 2-arm spiral. So yeah, so if you want to expand this analysis on other streams, we will have to sort of know, you know, the full orbit of the stream.
Yeah, because it really is a timing thing, right? When it comes to the
Yeah,
bar
yeah.
and how long your stream is at the point that it's passing through the disk. Yeah, so I was just, you answered my question because I was curious, can we start doing this for the other streams? But it's a little bit difficult since we don't have the 60 phase space information. Cool, thanks.
I guess just following on kind of the point Neil was making as well. I mean, there are some streams which it doesn't really matter. Like when we include the bar and spirals, it has almost no effect. So for those ones, yeah, it's not going to affect us. I had a question for the cosmological simulators. If I think Andrew Wetzel wasn't here, but others as well. So I guess I'm wondering, like, when it will be possible to kind of resolve some of the things that we're discussing in terms of baryons, like GMCs and, you know, spiral arms and bars, and whether or not we should not at that point yet where we can kind of use them as our realistic potential to disrupt streams in, and then try our extraction processes. So are there any kind of simulators in here that can answer that question?
I could speak just for what we've been looking at briefly. In terms of GMCs, yeah, we've actually had several papers now. That's something we're able to resolve, at least the massive end of the GMC mass function. And I think there's a lot of interesting work to do there, sort of just understanding GMC dynamics, lifetimes. These things are forming along spiral arms. There is spiral arm structure. I don't think we've gone all the way to test sort of how realistically the diversity of spiral arm structure is in these simulations, but it's certainly there in a visual sense. And then in terms of bar formation, I know Sarah's there. There's been a longstanding plan to do a deeper dive into this because we haven't really tried quantifying that more carefully. We looked at one case where there's clearly sort of strong bar structure, but it's not something we quantified. So I think there are bits of this coming into place, but you know, at least on our front, more work to actually quantify how similar these structures are to what we see in the Milky Way and nearby galaxies.
Awesome, Zephyr.
I was just going to say that I think trying to compare cosmological simulations is probably going to be quite an active meeting in the middle. We can probably ask questions of Sagittarius-like streams, but not the kind of streams that most of what we're thinking about in this conference is touching on.
Sarah Pearson.
Mine is a slightly different topic again, so I don't know if anyone wanted to comment on what Andrew said first.
Well, let me just raise what I said in the chat. I think it would be interesting, Andrew, to try to like pull out what the time evolution of the mass or the clumpiness of the GMCs that are in your simulations, what that looks like, and then try to use that in a stream simulation as a representation of the population of GMCs instead of just Hernquist spheres or whatever people are using now.
Yeah, so we've thought along this line, but I guess just to clarify exactly what are you thinking? You know, it's one thing to clarify sort of the clumpiness of the potential, but it sounds like you're thinking of going even further, of coming up with some representation of that you can feed back into Is that what you're thinking?
Yeah.
Yeah, that's a good question. That'd be a good thing to do. Yeah. We haven't quite got that far, but we've had some thoughts in that direction. That's a good idea.
Sarah, new topic.
Yeah, so kind of a spoiler for my talk tomorrow, but another solution is also to go to galaxies where we just don't have spiral arms, bars, or molecular clouds. And I think I haven't done the careful thinking yet of what we'll actually learn, but I think it's really interesting to think if we see gaps in a lot of other galaxies from thin streams, it obviously becomes a numbers game of how many do we need to see, and then going back to looking at subhalo distributions that we expect. Can we actually learn just from gaps alone without any kinematics, anything statistical about subhalo populations in other galaxies? So I think that's a whole nother route to go, which was only now beginning. So I don't think we have that answer yet, but I think it's a fun problem to think about, that there are galaxies out there without these problems. And for context, we haven't actually found thin streams in any of them yet.
I've got a kind of new topic question as well about, so I mean, I'm going to call Chiati's mechanism, and I guess Ray Carber's mechanism, a baryonic effect, because it's just a big enough dwarf that I'm going to call that baryonic. But how can we decide if this thing is really happening, where you have the globular cluster disrupting a lot inside of a dwarf galaxy before it starts disrupting onto the Milky Way, and that just makes a crazy debris field? Anyone want to take a stab at that? All right, I can also take a stab at it, but
I guess we could. Sorry,
Eduardo, go ahead.
Yeah, I didn't raise my hand. Sorry. I guess we could try to look for a chemical signature of the host galaxy, right? Because if it was big enough to have a globular cluster, certainly it has some few stars to it. So I guess that would be one way of at least pinpointing that it could have come from this sort of scenario.
Cool. Rodrigo.
But can we be absolutely certain that there'd be any field stars? I mean, these systems might have been formed, the globular clusters might have been formed by collision of gaseous clouds within separate dark matter halos, right, mini halos, and why not then have a globular cluster forming in that sort of way? It'll be slightly off-centered from that subhalo, and then you have exactly this crazy debris field with perhaps two such systems in it. Why not?
I think that's a good point. I think that's very.
I guess the absence of these in isolation, I guess, but I mean, you're right, it could exist.
Cool. Rodrigo, is your hand still raised, or is that from the previous time?
Sorry.
No worries. I guess one other question I have, kind of related to some of this, kind of the past, is, like there are many objects in the Milky Way which we can see that are quite compact, which could perturb streams. So there's globular clusters and dwarf galaxies, and each of those, if they did hit a stream, would be hitting it in an arbitrary place in the Milky Way. And I guess I'm wondering, how much can we trust our backwards integration Milky potential to really know what something was, let's say 5 gigayears ago? Because some of the streams can really, almost fold on themselves. Like there's some examples with SAG interactions on GD1, and you just get like a parallel stream pulled off because it's folded over, basically. And that can be a very old interaction that then moves down the stream. Mark, I think your hand was up first.
Yeah, I don't have an answer to that, but I was actually thinking about a similar question. So maybe I'm just reinforcing your question, but I'm getting increasingly worried when I see all these results of people, including the LMC and Sagittarius, that perhaps all that backward integrating is fine until you interact with any of those larger satellites, right? So beyond an age of a few gigayears, perhaps you're almost in a sort of planetary chaotic limit where it becomes almost impossible to say with certainty that it wasn't a globular cluster or another halo member that crossed your stream, because within the uncertainties of orbits, perhaps anything will have had some interaction with some of the other satellites. I don't know if people have tried to quantify that, but it's a concern I have when you ask that question.
Guillaume.
Yeah, so for me, it was also the same kind of question, also a reflection about the number of dwarf galaxies also that we have discovered. Like for the moment where with new spectroscopic data, we are recovering also in phase space new structures of previous galaxies that have been existed. And we are just looking for the biggest one, but in the future, we know that we almost with a lot of probabilities going to discover new residue of dwarf galaxies already are created as well that have also kind of modify these different orbits, kind of generated also different kind of effects. So I'm just wondering at which, again, like, yeah, which ages are we able to trace back the orbit, knowing also that due to the entropy effect, at some point we are not able to reproduce everything in the back, everything in the past.
I think that's a really good point. I mean, just want to make one point really quick before we go to Eugene, but one way to like perhaps look at that would be to have realistic cosmological simulations, which make mock observations of in like similar resolution, and then see how well you can understand the past of that simulation without having seen it, for example, to get a sense of how badly we know the past. Eugene.
Yeah, just to answer Mark's question, I think it's not so much, or not only the uncertainty in the orbits, but also in the potential that we're integrating back, right? So have to keep that in mind. Beyond a few giga-years, I don't think we have any strong constraints on how fast, how far any given orbit will be on its orbital phase.
Yes. Yes, that includes the potential of the LMC and Sagittarius, right? Which we don't know with high certainty giga-years ago.
Absolutely.
I mean, the LMC is hopefully very far away in the past, but that's kind of.
In most cases, yes. Yeah. Well, one of the reasons why I only followed the last 3 giga-years, because in some cases, the LMC returns back. If you look more than 3 giga-years ago, I did not want to that.
Sherman, you're up next.
Yeah. I mean, two things. I mean, just maybe a comment and then a question. But since you brought up like the issue about getting realistic cosmological simulations, I'm not actually that convinced about the need of having waiting for the next realistic cosmological simulation. I think like the cosmological simulations are already as realistic as they get, but the thing is like, how do we actually harness the information that's already in them? Pertaining especially for like things like with subhalos, I think a lot of the subhalos that actually fall onto the Milky Way are somewhat sort of resolved down to a certain mass scale, but it's just the later evolution that isn't. But the cosmological simulations do give you the initial conditions, the realistic initial conditions, at least at infall. And I don't think that the issue is that we need to wait for another cosmological simulation that will actually resolve like globular clusters to answer any of this. It's just how do we actually use the information in the smartest way possible, rather than actually just wait for more computer power and like killing the Earth some more. And then the other question that I have is relating to the globular clusters, because I agree with what Sarah brought up about thinking about looking for streams in external galaxies. But I wanted to ask the question in terms of for our Milky Way. I mean, we now have like quite a lot of information about like the various globular clusters that are around us, and we're probably just not detecting some streams in some distant globular clusters. But did anybody like think about like sort of a like a golden list of like globular clusters which we should watch out in the future that are probably further out and would not be prone, for example, to baryonic effects, and would be like sort of the best targets to study interactions with dark matter subhalos. I mean, I'm just asking this in a very naive way because I didn't really follow this up, but I'd be interested to hear what people have to say.
Yom has said NGC 5466. I think the next few questions probably don't plan to answering the second part of what you're saying. I think that's a good point about the kind of using what we have already with simulations. I will say that in terms of like golden globular clusters, that many of us did look at globular clusters that have tidal radii that are close to their their kind of scale radius just to see if those are disrupting a lot, at least with Gaia DR2, and it was very difficult to see any obvious streams, although that was 2 years ago, and now some work has found more streams around that. I think Andrew is next from my accounting.
Yeah, so I agree with line of thought, both in the concern about how far back we can integrate, and also that I think there's a lot we can do with sort of the current generation of simulations, which is something we're starting to try to test against. But related to this point, and to the point of differentiating, subhalo interactions from sort of disk level interactions, I'm wondering what people's thoughts are about the precision with which we can age date a perturbation on a stream, because it seems like that is going to be a key point, right? So, if we think that the perturbation happened 4 or 5 gig years ago, right, then I think I'm very concerned about this. If it's less than a gig year ago, right, then I think the problem is much more tractable. And similarly, right, if we can sort of cross-correlate age dating with pericentric, passage near the disk, I think that would also be a very powerful lever arm for disambiguating sort of disk level versus sort of more outer halo interaction. So it seems like that's an important question. And I just don't know what people's current thoughts are about what kind of precision we can get.
Yeah, it's a great question. I mean, I'll just answer that very briefly, and I'll let Adrian take a stab at it as well. But yeah, so when we fit gaps in simulated streams in the 2015 paper, try to figure out the age precision, it was in the kind of 10 megayear range. So we were able to get very good idea on when the interaction took place. But again, that was in simulated streams. We're now trying to do the same thing with the Atlas stream with Tara Kilme. So we'll figure out for that one. But yeah, so it was very precise. Yeah.
Just to clarify, that's 10 mega years, regardless of whether the interaction was 500 million years ago or 5 gig years ago.
The interaction here was, I think it was about 500 mega years ago.
Okay.
But we are going to test to understand how well we can age date different ones. Yeah. Adrian.
I was just going to say that for GD1, we found that trying to just fit the gap, it's multimodal. You have solutions that go back as quite far back in time. There's other things that limit the size of those modes, but things like the spur or other like indications of recent encounters and being able to measure velocity differences between the stars and those things and the main part of the stream track. Those can really pin down the age. It breaks some of the fundamental degeneracies you have in the parameters when you just observe a gap. So I think, I mean, from my perspective, I'm a broken record on this, but I think the off-track features, like the signs of recent encounters, are going to be the most powerful for getting age constraints. But
cool. Just want to reiterate part of Adrian's point, that what I was talking about with this age determination, that required multiple different types of observations. It wasn't just a gap, it was gaps plus radial velocities plus one other observable, like track on the sky. So just with the density, you won't be able to do it. But if you have multiple observations in different dimensions, then you can get at it. Zephyr is up next.
Yeah, I just wanted to flag up one other possible baryon effect, which maybe people here could say that it's not important, which is baryon effects in the stream itself, like compact objects and possibly even stellar evolution or the collapse of triples into binaries. All these things, especially when the stream or the progenitor of the stream is down to a small number of stars, I can imagine can produce some gaps and some kinks, and I wonder whether that can be effective.
Any takers on that, like Mark maybe, or someone else want to chime in on that one before we go to Ting? Mark?
Yeah, I haven't looked at it in detail. I would guess that it's very difficult to get substantial differences in the structure of a stream from self-gravity. I think they're not self-gravitating. Once the stars leave the cluster, they would care just about the galactic potential and not so much about. But you raise an interesting point. Perhaps if black holes are more massive and they are in between them, perhaps they could deflect orbits. But whether it would really create underdensities or overdensities, I doubt it. But it's a bit more of an intuition rather than an actual fully justified answer, I'm afraid.
Ting.
Yeah, so my question is kind of related to what was discussed earlier. So I feel like for like a GMC's bars, like we can do something with the cosmological simulation by like ejecting a group of stars and that it evolves and then see how it evolves over time in the future. But for this internal thing that the globular cluster like form in subhalo and then have this own kind of thing. Is there a way even we can use cosmological simulation to help us? Or in other words, like what kind of, the other way to ask the question is like, if it's coming from a dark matter subhalo or from a GMC, at least we kind of have some idea in terms of like the correlation between the morphology and the velocity, for example. But for these internal heating, do we have any clue about what kind of observation signature we will see and using that observational signature to constrain that kind of thing? I don't know if we have the tools or we can have the tools to do any of that, either from the analytical way or from the cosmological simulation. And I would like to see the experts how to address on that. And related to that, so when I'm saying internal heating is really saying the interaction between the globular cluster and its parent halo, but also like whether there are differences in terms of observation on like internal collision of the globular cluster, evaporating versus stripping. Is there also difference in the observation observables, I guess?
Cool questions. Any takers for those questions? I guess I can kind of partially, I don't see any hands raised right now. But yeah, I guess, I mean, for the effects from like, you know, the dwarf host, if it's had many orbits, like if the globular cluster has been orbiting for a long time around that host and then it gets stripped around the Milky Way, I think it's going to produce an extremely complicated debris pattern that probably we wouldn't be able to resolve, to be honest. I mean, at least I don't think, at least from what I understand. But we could perhaps just get a sense, you know, either from cosmological simulations or perhaps more realistically from more examples like what Kyachi was showing, you know, what the kind of broad features look like. But I think matching an individual set of features by kind of rewinding and getting the orbit around the dwarf right is probably impossible or extremely difficult. It must be very chaotic.
But how we can do this statistically? I mean, if we cannot do individually, I just feel like, I don't know, I start with whole day is like, I feel like, yeah, GMC bar, spiral arm, they are things we should consider, but I feel there's a way at least to solving those. But for this, the parent halo interaction part, I just don't even know there's a way we can model that. And I would hope that cosmological simulation can tell us of some of that, but then we need to eject globular cluster inside of those dark matter subhalo, let it evolve, and then to kind of compare with observation. Then it can become like super complicated, like what Monica mentioned yesterday. Like we are always making everything more complicated. So that's why I feel like if there's actually a way of we can do, or the direction for a way we can solving this problem.
Adrian.
Just to echo Eduardo's point, I think an important part of that will be detecting those systems in isolation, which will be a challenge, but I think will be important in order to, like, you know, assess the importance of that effect. And I think it's reasonable to assume that we will at some point have constraints on that from looking at, you know, light versus lensing signals, you know, offsets in smaller and smaller systems over time. Ting, did you want to respond?
Yeah, so I actually, when Rivaldo mentioned about like using chemistry to find the cleaner ones, I actually don't understand this very well in terms of, I would expect the dwarf galaxy get disrupted first. So even I guess my question is, even a global cluster had interacted with its parent halo in the past, but do we necessarily to see the parent galaxy's star member surrounding around the global cluster? Do we know that? If the dwarf galaxy gets disrupted early on, and so they are at a different part of the sky, then even there was some interaction in the past. We don't necessarily have to see the dwarf galaxy stars presented in the region of the globular cluster stars. I don't know, maybe there are some simulation doing to show that. I actually asked a question about this, I think in Kian's, in Kiadi's work, but I don't know.
Yeah, I agree, but I'm just saying, like, until we detect a system in which it's a globular cluster rattling around in an empty, otherwise empty halo, I think we should think of it as like a possible effect, but we don't know that they exist, right?
Let me ask the other way, maybe like using either the GD1 case or the Atlas case. So we can explain them now by throwing in a dark matter subhalo, or maybe we can explain some of those by Sagittarius globular cluster or Sagittarius. But can we explain any of these from just the internal heating? And if there are any models we can do to map with these observations? I guess that's the question I have. And if there are some simulation we can, like, say, letting a globular cluster evolve in its parent halo and then get disrupted, and then match in both the velocity space and the on-sky morphology space, that it's the perfect match. In other words, they are indistinguishable between a perturber versus internal heating. Or maybe the kinematics are totally different, so we can separate them. I don't know. That's kind of the question.
Yeah, I think that's a great point. Unfortunately, I think we have to, I'm about to close the breakout room. So someone else closed them. Okay. Anyway, let's plan to raise that and continue discussing that with the bigger group. See you all back in the main room.
So we actually identified quite a lot of good things to aim for in terms of ruling out or disentangling baryonic from dark matter effects. And that was mostly what our discussion focused on, because I think it was more or less agreed upon from the start that for baryonic perturbations, we have a better chance of tracing individual stream perturbations back to a baryonic source, since those are things we can actually observe. So we talked for a little bit about what, and Monica posed a question about whether there's good, like what kind of evidence we have of giant molecular clouds affecting streams, for example. And in talking about that a little bit, we need to be more conversant with sort of things like the mass size distribution of GMCs and what their internal structure is compared to dark matter models. And so an area where the dark matter theory, I think, still needs to work is in understanding for different dark matter models what the perturbing subhalos, density profiles, abundances, etc., are likely to look like by the time that they assemble and then get transformed to the point where they're perturbing streams deep within the halo, which is where we're looking now. So as Matt Buckley put it, that transfer function varies per dark matter model and is better understood for some than others, and is impacted by the growth of the galaxy in the center, which isn't in all of the descriptions that we have yet. Not only that, but the geometry of the impacts is also important. So we need some better models for that as well. And that may help us disentangle baryonic from dark matter interactions when we can tell by the geometry that the source of the perturber was somewhere with a high concentration of baryons. We talked a little about stacking signals to try to get some average templates for different kinds of events. For example, if we can find a few perturbations that we can clearly link to a particular baryonic perturber, then we could try to compare the signatures that those leave to ones that we don't have evidence for and see whether they resemble each other, and try to build up some sort of intuition that way. There was a sense that in order to conclusively prove that something wasn't or was dark matter, statistical constraints may not be enough, that we'll actually have to have some particular thing to point to. And we talked a lot about how to bring in better priors for various aspects of the dark matter distribution, which is another place where I think theory still has some ways to go, both in terms of the main halo, where on the observational and modeling side, we don't yet have a great handle on the mass of the Milky Way, and neither do we have great handles on the masses of the largest things that have merged with it lately, like the LMC and SAG. And so all of those are limitations that keep us from understanding how the presence of the LMC, for example, affects what we would expect from subhalo interactions. Since without a better constraint on those properties, we don't really know what proportion of the Milky Way's subhalos should come from the LMC beyond sort of an order of magnitude, which is not very constraining for these purposes. And finally, I think the other thing we talked about a little bit was knowing more information about more progenitors of streams, because this is so valuable in understanding how to infer something about the velocity dispersion of the stream and whether it's what we expect. And in terms of the ages and orbits and orbital phases of stuff that we're analyzing for perturbations, which are all interlinked and sort of quasi-degenerate in terms of modeling individual perturbations or understanding the evolution of the velocity dispersion. And as Monica pointed out, velocity dispersion is particularly tricky because you have competing effects. On one hand, you have Liouville's theorem, which means that a stream in an analytic, completely smooth potential will get colder over time. But then you have lots of other things that could heat it up with various interactions that we need to be aware of. So those are sort of the stuff that we outlined that mostly fell on the theory side, but with a few things that observers can go out and try to measure better.
Very cool.
I don't know if anybody feels like I missed something from that discussion that wants to.
I don't see any hands raised, so I'll just kind of briefly discuss our one as well. So yeah, someone has excellently actually summarized what we talked about and kind of broken into sections. That's very helpful. I see Adrian smiling. Maybe that was Adrian. But basically, yeah, we tried to really think about kind of the ruling out aspect. How can we rule out individual baryonic effects? And I think, you know, Robin's point was very good, that the baryonic side is a side that we can know extremely well. And so we can hope to be able to rule in or like rule out those effects. So we started off with the discussion on, you know, Milky Way disk substructure. So things that are in the disk, like the bar, spirals, GMCs, talk about how we could rule those things out. And so what's nice is that there are already some streams where we can like rule out most of those effects. So for example, GD1 and Atlas, we've looked quite carefully at all of these effects. And at least with current implementations, you know, by marginalizing over our uncertainties, we can see that there's no effect from those. Now, to be fair, that, you know, when we do this, we're always assuming some things about, for example, like GMCs. We don't necessarily know exactly how they looked in the past, or, you know, their precise features. So there's still work to be done there, but there is a kind of, you know, program going forward for at least some of the types of perturbations. In terms of, you know, again, once again, ruling out disk substructures, one point that was raised is that at least in the current fits where we try to fit individual gaps in what they were due to, we get a relatively precise time resolution, at least if enough observables are brought together, about when the interaction took place, and that can help you understand whether or not it was in the disk plane or not. And so if you find a perturbation which has been assigned to the disk plane, you should be very worried that it's something in the disk. But that's a kind of way of, let's say, ruling out disk structure. We talked about, you know, the kind of globular clusters, dwarf galaxies in the Milky Way. Obviously, there's many objects orbiting around. And how can we know if those objects have or have not perturbed a stream in the past? And so we talked about kind of uncertainties in the past orbit of something and how well we can possibly know the potential of the Milky Way. And it becomes an issue over some time scale in the past. We're not 100% sure of when, but obviously once you go back many, many gigayears, it's a problem. And for a short amount of time, probably it's relatively okay. But this issue of like, how well can we actually know? So for example, like with Sagittarius, we had some examples of SAGE impacting Atlas and GD1 with kind of fairly flexible past orbits of SAGE. But now that we're using, models that reproduce the SAGE stream, we're not finding those anymore. And so the question is, have we allowed enough flexibility or not? But by really understanding the past history of the orbits of these things, we can try to figure out whether or not, let's say, the classical dwarfs or the ultrafaints or the globular clusters have caused effects in the streams. We talked a bit about, the Milky Way and LMC and in that aspect as well. And kind of, that we don't exactly know, the past beyond some time scale. I guess one point I do want to add there is that, based on everything we know about the LMC, it is moving away from us quite quickly in the past and in the future, I guess. So probably its effect is relatively, recent in that respect. So for example, like the subhalo parts of it, probably just coming in for the first time. And I think also Andrew Wetzel mentioned that in the comments. Talked about the kind of picture from Ray Kalberg and Kjoti Malhan with this kind of complex morphology from the dwarf galaxy and globular cluster falling in together, and how that was actually pretty hard to rule out. One kind of way that we discussed of not ruling out, but of, I guess, saying it's okay, is if we could find the dwarf galaxy debris, from that dwarf somewhere near the globular cluster, although we weren't sure that you should even expect to find dwarf galaxy debris there necessarily. And then, we kind of discussed the point that if we don't find any dwarf galaxy debris near any globular cluster streams, maybe that's kind of a bit not problematic, but it just makes us think more about whether we can really understand that. We discussed kind of how we could model this complex morphology, and we decided it was very difficult to model, like in a nice like a way to actually match. So we kind of ended that in a way that wasn't unclear. And we kind of ended off, well, not ended off chronologically, but just chronological, I'll say it this way. Kind of finally we discussed streams in other galaxies with different baryonic components. And so if we can see streams with gaps, let's say in galaxies that don't have disks or spiral arms, that could be a nice way of showing that we really are getting dark matter when there's no possible baryonic effects that can matter. So I think it was pretty good in terms of ruling out certain aspects, although obviously a lot of work is needed to be done. Cool. Let's open it up to questions and discussions then, and points you want to make. Anyone want to raise their hand and ask some questions, make a comment on things we discussed? Sarah Pearson, yep.
Yeah, just one point that didn't come up yet is that, for example, for PAL5, which we know is prograde with respect to the disk and bar and comes close enough to be affected by these baryonic components, we actually still don't have a complete sense of a simulate, or we don't have a simulation that simultaneously reproduce everything at once. So the gaps and the fan and the wiggles in the track, we've all just showed that dark matter subhalos and the bar can create these features. But just for context for everyone who's not working in detail on this, that even for the streams that we know very well and can trace back and even know the progenitor of PAL5, there's still work to be done in timing the different features.
I guess one thing which we didn't discuss, at least in our room at all, was that we can actually use the streams to try to understand the baryons better, in the sense, for example, we could try to map out the bar's pattern speed and the effect it's having by combining many streams like PAL5 and Ophiuchus. By having this kind of coherent picture, we can actually do better than we're currently saying. So there's also, like, I think we didn't discuss this, but it's something that can definitely be done in the future, is to really nail down the baryons better, so we can know what they did and didn't do. Sarah.
Yeah, just another point about the external galaxies, how it could be great to look for gaps in thin streams in other galaxies than the Milky Way. One problem we'll still have there is that such other globulars could still perturb the streams and create gaps, and that can happen obviously without the presence of a disk and a bar. So that's something we've had a chat here in the notes you can see to the right, and we're summarizing some of it in Slack now. But I I think tomorrow would be interesting to discuss what we could maybe learn by having enough thin streams in other galaxies, where we could start seeing gaps as a function of galactocentric radii and tying it all back to expectations from Andrew Wetzel simulations and other people's work.
I guess I have a question for the kind of observers, perhaps. I mean, a lot of the discussion in our room was on the theory side and like understanding each of the aspects. Like, do the observers feel like they know what the theorists want, or do they feel like it's just super unknown? We just want everything better. Like, perhaps this was discussed better in the other room.
Josh says no, and we discussed a lot of theory stuff too.
Yeah. I mean, I think.
Although I think there's a universal sense that like finding some more streams with progenitors would be good.
Said he heard everything. I think that's accurate. Yeah, we need everything better.
Yeah.
So I think for the large scale structure.
To every star, please.
I think for the large scale structure we discussed yesterday, it's a bit more. Yeah, I think having streams further out helps. But yeah, for the small scale perturbations, we really do need like very precise radial velocities and yeah.
Yeah, so
accurate.
Alex brings up a good point that RL Lyrae, it could actually be doable. I mean, LSST will just find all the RL Lyrae in the galaxy. Like we'll know which ones are RL Lyrae from LSST in like the first 2 years or something, right? So that's a really valuable resource that I think, even though they're pretty sparse in these targets, is really good because it gets us a local calibration if we find one in a stream.
Ting.
So I understand that if we measure the R Lyraes in the stream, it can help with like the yesterday's talk on potential constraint, but how that helps the substructure? Are you expecting like saying like one of those gaps has a R Lyrae happen there and you want to use that to measure? I'm not sure if like one particular star is enough for that.
It's because the distances come into all the different space velocities and spatial positions. And so if you have a good distance calibration, even at one point along a stream from RL Lyrae, it'll translate into improvement, I would expect, along the whole stream for all the other stars that you can observe. That's sort of been my thinking on that topic. But I don't know whether that's I would like to hear from some people about how realistic that is.
Adrian.
Yeah, I was just gonna say I've gone off the rails a little bit in the chat. Sorry, it's only Wednesday, but but I think we need the balance between having good coverage of like all of the systems that make up the halo, and we need better signal to noise over the background halo for individual features and individual streams. So we need both, and I think we need to figure out how to balance those things. Like we can do a lot with 60 phase space plus kinematics plus chemistry plus ages for modeling, say, the spur of GD1 or other intricate features like that. We might not need all of that information for every single star, but there are certain regions where we do need all of that information, and we need to figure out the prioritization between those things.
Ting.
So yeah, related to that, that's the question basically Dennis asked, if an observer understand what a theorist need. And so I understand one side is like try to get as many stars as possible. I think get a certain amount of a star in each stream to use them to constrain the orbit for the science that we're interested in yesterday. So for this one, is that correct? What we want is, first of all, is identify those features, and second is get good kinematic data and maybe chemical data and at these features. And in terms of precision, I'm hearing that we want to get sub-kilometer per second precision, or even better, maybe after average in all the stars, which means we need to go deeper in those kind of features. Anything else? And maybe also, do we need like anything else we need? Like, do we need to get like a much better proper motion beyond Gaia gives in this area, and how realistic it is doable with, say, HST follow-up or with future LSST, Rubin Observatory observations, and anything missing here?
Eduardo.
Can I go on, Eduardo, and then I'll comment. I'll put my
Yeah, not sure if totally related, but soon we'll have very deep photometric surveys, and we'll be finding streams on the sky only, right? And we'll be running back to the same issues that we had before Gaia and large spectroscopic surveys, where we would question every gap that we see, or can we actually have some additional information that allows us to get better membership without expensive missions like Gaia and big spectroscopic surveys.
Robin.
Okay, I have 2 comments. First, I think it's going to be useful to keep an eye on what Roman is observing once it comes on sky, both because there will be coverage of areas that have streams observed in HST, and therefore a long baseline proper motion measurement is possible there. And also because there's a big patch of the sky that is at high galactic latitudes, it's going to be covered for weak lensing survey, guaranteed over a 5-year baseline, and even from just that, decent proper motion much deeper than we got with Gaia. Sort of like the quality that you get at the edge of the Gaia volume, but extended farther out. So that was point number 1. Point number 2 is I think some people in the chat especially were talking about zooming in on the parts of the streams that we see that are disturbed. I think we should also be sure to observe in the same detail places where we don't see disturbances so that we have some sort of baseline. Because I think if we just have data at different levels on the parts of the stream that we think are important versus the parts that don't seem important, we're going to run into some problems. And finally, Adrian mentioned ages, and I said this in our group, but I want to just point out again that from what we're seeing for dwarf galaxy streams in cosmological simulations, the correlation between the age of the stars and the time when the stream starts to form is extremely loose and extremely mass dependent. And so I would treat those brackets as very broad priors. So if you want to know more about that, then you can look at the paper that we're about to submit, and it will be on the archive in like less than a month. But generally, there's not a good correlation between the ages of the stars and when the stream started to form.
Awesome. Yeah, I think that for the question about proper motions, yeah, I will say, I mean, if we can get sub-kilometer per second proper motion precision at that distance, that would be helpful. I think that's not perhaps as easy, apart from a few streams that maybe that have HSP pointings. But, you know, I mean, we need to, I mean, so like when we try to model streams of perturbations, we have to know both like large and small scale features, right? Because you have to get the overall orbit right. Like the Atlas stream, for example, has been deflected by the LMC and has a kink in it. And so we have to model the LMC's effect. For that, we need to have more data along Atlas, and then we need very precise data, you know, close to the kink in order to get that feature right. Rohan, I think you had your hand up briefly. Yeah.
Yeah, I wanted to speak about ages. I think ages from like main sequence turn-off stars that are that get you basically precision of like 10-ish% when you like model them, like, you know, along with the spectra and the photometry together. I think are really important, like in terms of setting these brackets, right? Like, because they're giving us for the dwarf galaxies that are bringing in the globular clusters that are then forming the streams. I think they are pretty, they rule out like large swaths of parameter space, which I think is still very much worthwhile to do. Even though I agree that in some simulations with certain, like, you know, models for galaxy formation and gas retention and certain subgrid recipes, you might have like certain ways the gas is being retained and you're still forming stars. But getting that data of ages of stars, I think, is still very worthwhile for these dwarf galaxy streams.
I had one comment to make, kind of inspired by Eduardo's talk and kind of some discussion in Eduardo's chat yesterday, but it's about, maybe that was 2 days ago, but it was about if we can tell where along the stream stars originally came from. So some of the perturbations which we're currently discussing involve moving stars way downstream. So some of the GD1 perturbations with SAG, for example, those stars started way on the left-hand side at like phi 1 of minus 100 and have then moved down the stream over time in order to be where they are today. So if we could know where those stars came from through like the mass function differences, or maybe if it's a dwarf galaxy stream with something like, you know, metallicity gradients, that'll be really helpful. But I know that's a very big ask, and it also depends whether or not there even are mass function gradients in streams. But it's another type of observable that could really help with disentangling, you know, because, you know, when you perturb a stream, like things will move downstream for a very long amount of time if it's a small kick. And so you, like after a giga-year or two, you may have stars that have moved, you know, 30, 40 degrees, 100 degrees. So it'd be really cool to be able to unwind that chemically or through mass functions, something like that. I have about 3.5 minutes left. Anyone to bring up something which they think hasn't been discussed, or perhaps, you know, we've discussed a lot of different aspects today, but is there some aspect that you think we're missing out on? Anna.
I wanted to upgrade some of the conversation that was happening in the chat, I think spurred by Josh. And I think Josh posed like really good questions of the like the kinds of questions we should be answering in order to move forward. So maybe Josh, can you like tell us like what would say get Mega Mapper funded? Kind of what sort of theoretical predictions could kind of help this effort?
Well, I mean, I think at the moment, you know, there's a lot in the US that's in the hands of the Decadal Survey. And we don't know what they're going to say, but they will say it relatively soon, and that will make it a lot easier to know what the broader landscape is. And I don't think that there's anything that we can do in the next 2 months that has any impact on that process. That's already passed. So I think for the moment we're in a bit of a waiting period. You know, in the broader sense, I think, yeah, as you were suggesting, having the most detailed forecasts of various things that we can, that will provide strong motivation for specific science cases.
Cool. Yeah, I know there's some kind of efforts that are underway with that. I think one of the things that we discussed yesterday that would be really useful is to have, you know, realistic mocks where we can really test each of these aspects. We discussed this yesterday in the context of, you know, how well we can measure large scale structure. And, you know, I think we probably need to do the same thing also, obviously, for small scale structure, and really test each of our approaches and see how robust they are, because it really matters if there's any biases in our fits. So perhaps it's a good thing also to discuss on Friday with the kind of community efforts. In the last minute, any kind of final comments?
I just wanted to say thank you to everyone. Today it was great. It was a total whirlwind to try to keep track of all the different places that people were engaging. But I think this discussion has been really useful. And I think the days are kind of naturally, I don't know if we did this on purpose, but it's from like the oldest ventures and streams, finding them, to the larger scale characterizations. Now we're on small scale, which is a more like a newer venture. So I think the discussions are a lot more freeform and contemporary, at least. So thank you all.
Yeah, thank you.
And thanks especially to Robin and Dennis.
Yeah, thanks to moderators. Great job.
Thanks to the organizers also for a fantastic conference in general. Yeah, it's very fun and interactive.